All right, before we start today, I want to take a quick look at the exam results. So not surprisingly, they were lower. So the first, just to sort of calibrate you, in the first exam, we averaged 13.9, so we dropped by about 3 points out of 20, roughly 15%. So that's a significant drop, but not unexpected given how things usually go. We were a little bit lower than last year, but our first exam was a little bit higher. So basically, right now, things are on average about the same as they were last year. The university, made the deadline for dropping classes absurdly late, in my opinion. So you have still a couple weeks to figure out if you want to stay in the class versus dropping. I'm happy to discuss those options with you and what you should consider. We won't have another exam before the drop deadline, so you do have to decide based on your results for the first two exams. And although we still have 54% of your grade left from the third exam and the final, so really everybody in this class, no matter how you did in the first two exams, could still pass the class. Mathematically speaking, it's not particularly likely that you'll have a dramatic turnaround in the last month unless you really change your habits. So definitely come talk to me about that if you're not sure what to do. But keep in mind that we still have a long way to go in terms of the number of points that are left on the last two exams. So however you did on this exam, there's certainly an opportunity to recover from that. So the average was 10.8, 54%, and two students got 19 out of 20. There were no perfect scores this time. We did have two with 19 out of 20. All right, so that's just a quick rundown of that. I know some of you are curious to see how you compare to the rest of the class, so this is the breakdown here. But let's get right into the material then, where we're gonna continue talking about the behavior of gases, what are called ideal gases. We'll kind of define more specifically what an ideal gas is next lecture. But what we're going to do is, if you remember last time, we spent the second half of the last class talking about different relationships involving the properties of gases. So there were three relationships built off of how the volume of a gas responds to the other three parameters that we considered, which is pressure, temperature, number of moles. So we had three individual relationships, and it's important for you guys to know the terminology associated with those. But as we'll see today, what we're going to do is actually combine all three of these into one equation, and then that equation can always be your starting point whenever you're doing some sort of numerical problem involving the changing conditions of a gas. But just to remind you of what we did last time, we started with Boyle's law. And this one says that volume is inversely proportional to pressure. So volume is proportional to 1 over the pressure. So that was Boyle's law. The second one we covered was called Charles's law. And that one says that volume is directly proportional to temperature. And so we watched some videos that kind of demonstrate these first two. But mathematically, those are the relationships. As a reminder, temperature has to be in Kelvin, absolute temperature units for this. And then we also close with Avogadro's law, which was a pretty intuitive one, which says that the volume of a gas increases if you have more moles of that gas. And so then we write that mathematically as volume also being proportional to n, the number of moles. So those are the three individual relationships, and like I said, you should probably know what they're all called, because there could be at least conceptual problems that deal with that. But what's going to be useful for us to do numerically is to combine all three of these into one gas law. So what we can do is we can take all of these. We have volume being proportional to three different things, three different terms, and we can combine these by taking the product of all three. So this is a math trick that we may have done once before, but here is where it's going to be most important. If volume is proportional to three different things, it's going to also be proportional to the product of those three things. And so then what we can write is that volume is proportional to 1 over the pressure, that's from Boyle's law, times the temperature, that's from Charles' law, times number of moles. So we have this proportionality now. And it turns out that in terms of sort of defining the state of a gas, these are the only four things you need: volume, pressure, temperature, number of moles. So we can get rid of the proportionality sign. Before we do that, we can cross multiply so we don't have anything in the denominator. So we're just going to write it as, we're just going to cross multiply by pressure on both sides. So pressure times volume is going to be proportional to n times T. So this is an alternative way of writing the same relationship. And then, as we also talked about last time, if you have a proportionality and you want to make it an equal sign, you just have to put a constant on one side of the equation. So we'll put a constant over here on the right side, and we're going to say then that pressure times volume is equal to N times R times T, where R is the constant that we're using. And what's useful about this equation, this is called an equation of state, meaning that this tells us everything we'd ever want to know about a gas. It defines, you know, every possible parameter that we can measure for a gas is defined in this equation, which then also means that this constant here that we put in R is a universal constant. It's going to be the same number for any sample of gas. Doesn't matter what the gas is, doesn't matter how much of it we have, doesn't matter what any of these individual variables are. R is going to be a constant value of 0.0821 liter atmospheres per k mole. So this is a constant that is on your periodic table. There's actually two values of R. We briefly mentioned this earlier because liter atmospheres is also a disguised energy unit. So there's a value of R that's also in terms of joules that we will use a little bit in Chapter 9. And you'll use it a lot in Chem 2. But this is the value that we're going to use for gas law problems because this is in terms of the usual units that we use for gases. Liters for volume, atmospheres for pressure, and then of course we have to be in Kelvin, and the number of moles is just number of moles, no real variation there. So we call this value of R, this constant R, the universal gas constant. And as I said, it's universal because it applies for any ideal gas in the world. It doesn't matter which ideal gas we're talking about. So you don't need to know what the gas is. It's going to always be that value of R that we're going to have. So this is called the ideal gas equation when we put it all together. Ideal gas law is sometimes also referred to, and it's PV equals nRT. This is the very familiar equation that you've probably seen if you've taken chemistry before. And that's what we're going to use for a lot of different types of problems. And so then what we're going to spend for the next little while doing is just going through some different problem types that you could have that will start with this equation PV equals nRT. All right, so one type of problem we can do on this won't be the most common one or the most useful one, is we just have a single sample of a gas. We're not changing anything about it, and we just give you basically three of these four terms: pressure, volume, number of moles, or temperature. Just three of those four, and ask you to find the other one. So this one here, let's say we have a sample of neon, which is used in neon lights. That's not a misnomer. And if you have 0.1 moles of that with a volume of 2,503 milliliters, and you measure a pressure of 551 torr, what is the temperature of the gas? So this would be one where we're not changing anything about this gas. We're not changing its volume, changing its temperature, or anything like that. It's just a single sample of that gas, and we're just going to use PV equals nRT to find the missing quantity, which in this case is temperature, is what we're looking for. So in some problems, you're just going to take PV equals nRT, do a little bit of algebra, and solve for one of the terms, and that's all there is to it in many cases. So temperature is just going to be pressure times volume divided by N times R. So we just solve for that. Now the only thing you have to be careful about though when you're doing problems like this is if you're going to use an equation that has R in it, remember that R has very specific units, liter atmospheres per k mole. So you need to make sure that your pressure and volume are in the right units, and of course your temperature will come out then in Kelvin. So we have to make sure that we're aware of that. All right, so because R here, as we said, is 0.0821, straight off the periodic table. I think they gave it to one more significant figure than this, but that's enough for us. Three significant figures, 0.0821. And so what we need then is the pressure needs to be in atmospheres and the volume needs to be in liters, liter atmospheres, and none of those are true with the given information. So we have torr for pressure, milliliters for volume, so we have to convert both of those. So the pressure in the correct units of atmospheres is going to be, we take the 551 torr, and the one conversion factor that's important to know for this chapter is that 1 atmosphere is 760 torr. Those are the two most common pressure units. There are others, but those are the two that we'll see almost exclusively. And so that comes out to 0.725 atmospheres for the pressure in the correct units. And then volume, we just have to divide by 1,000. That we should be able to do in our head. But again, just to remind you, it's 2,503 milliliters. We use milliliters a lot in Chapter 6 when we're talking about aqueous solutions. For gases, it's more common to measure them in liters, although both are possible. And so 1,000 milliliters in 1 liter, so that cancels out, and we get 2.503 liters. So now we just have to plug everything in. Pressure in atmospheres, 0.725. Volume in liters, 2.503. Moles was given to us as 0.1, and that's going to be really the only unit for moles that we have. There's no really alternative to that. And then R is the universal gas constant, 0.0821. So every unit cancels out except for Kelvin, which will be the temperature that we get, and it comes out to 221 Kelvin. Now, I didn't specify a unit here, but if you had to convert that to Celsius, you would subtract 273, and it's minus 52 degrees Celsius, so pretty low temperature for this. All right, but that's just one type of problem you could get. You look at the information in the problem, and we give you 3 of the 4 terms, P, V, N, and T. 3 of those 4 are given. You solve for one of them, and that's just straight up application of PV equals nRT with a little bit of algebra. All right, so any questions on that? Now, the more usual situation for the problems you'll have in homework assignments and exams is one where you're changing something about the sample of gas. So we talked about these last time for those individual gas laws. We gave example problems of, Boyle's law, Charles's law, and Avogadro's law. And then there's also going to be problems like that where it's going to be useful to just start with the ideal gas equation. I would say no matter what the problem is, just start with PV equals nRT, as I'll show you how to do here, because then you don't have to remember all the different individual relationships. Or if it's not one of those 3, if it's not Boyle's law, if it's not Charles' law, if it's not Avogadro's law, you can always derive relationships between 2 or 3 of any of the other parameters as well. So you can always just start with that same equation, PV equals nRT, and then from there you're able to derive whatever mathematical relationship you need for that problem. Okay, so let's look at this one here. We have a balloon that has a volume of 255 milliliters with a pressure of 912 torr and a temperature of 25 degrees Celsius. And it's allowed to rise up into the atmosphere where the temperature and pressure are now minus 23 Celsius and 2.28 torr. What is the volume of the balloon under these conditions? So in problems like this, we have to take stock of, we start with PV equals nRT, and we take stock of which of these 4 terms, pressure, volume, number of moles, and temperature, which of those 4 are changing, which of those are constant throughout the problem. So in this problem here, we're telling you that the pressure is changing, 912 to 2.28, temperature is changing, 25 degrees Celsius to minus 23 degrees Celsius, and we're asking you what the volume change would be. So that's also going to be changing under this set of conditions. So the only thing that's constant in this is going to be number of moles. And again, we're not telling you anything about number of moles, and also it's a balloon, so as long as the balloon's not leaking, it's going to have the same amount of gas in it before and after. So we're going to then assume in this that the number of moles is constant. And it's really the only way we could do the problem, because we don't know how many numbers, we don't know how many moles there are, we're not told that it's changing. And again, anytime you have a closed container, whether it's a balloon or a closed rigid container that's not leaking out gas, you can assume that the number of moles is staying the same. Moreover, we're not telling you anything about that, so that's going to be your starting point, is the assumption that number of moles is constant. So once you identify what your constant parameter or parameters is, and there's more than one that's constant, then you're going to take everything that's changing and move it over to one side, and everything that's constant, you're going to move it over to the other side of this equation. So we're going to rearrange PV equals nRT to put everything that's changing on one side, everything that's constant on the other side. So R is also a constant. It's always going to be constant because it's just 0.0821. So we're going to put these 2 things on one side and then pressure, volume, and temperature on the other side, because those are the 3 that are changing in this problem. So we just have to move temperature over and say that pressure times volume divided by temperature is equal to N times R, and this whole thing is constant. So because this ratio PV over T is equal to a constant, then what that means, just like we've used for other simpler equations, is that that ratio before and after the change are going to be equal to each other. So P1 V1 over T1 equals P2 V2 over T2. So on some level, this is a combination of Boyle's law and Charles's law put together. But again, you don't have to remember those individually or combine them in a specific way. You just start with PV equals nRT and isolate the parameters that are changing on one side, and then set them equal to each other like we did here. So that's the equation we're going to use, and what we're solving for is the final volume V2. So then we have to do a little bit more algebra and say that V2, or you can plug in numbers first if you prefer. It's really up to you how you approach the algebra. But we're going to cross multiply by T2, so we're going to get P1, V1, T2 in the top. And then we're going to divide by P2, so we're going to have P2 and then T1 in the bottom. So we have those 2 ratios, P1 over P2, T2 over T1, multiplied by V1. And so now we're ready to put everything in. Now for problems like this, we dropped R out of the equation because it's a constant, and so we don't actually care about the units for pressure and volume. Temperature still has to be in Kelvin. That's non-negotiable, no matter what you're doing in terms of R. But pressure can be whatever we want because we have a ratio of 2 pressures, so as long as the 2 units are the same, they'll cancel out. We don't have to convert both of them. It wouldn't be wrong to convert them, but you don't have to. And same with, in this case, whatever volume unit we put in is going to be the volume that we get as our answer, so it doesn't have to be in liters. And then the temperatures have to be in Kelvin. That's the only one that we can't mess around with. So we can just start plugging everything in exactly as is given to us, except for the temperature, which has to be converted. Okay, so what we have is P1 is the initial pressure, 912 torr. So it is a little bit, you have to be a little bit careful to keep everything straight. Which one's P1, which one's P2, and so on. V1 is the initial volume, which is 255 milliliters. And then we have to put the temperatures into Kelvin. So T2 is minus 23 degrees Celsius. We add 273 to get it to Kelvin, so that's going to be 250 Kelvin for T2. And then in the denominator, we're going to have the final pressure P2, which is 2.28. And then the final temperature. I like to arrange things where the ratios are kind of lined up. So the 2 pressures on top of each other, 2 temperatures on top of each other, just so you're aware. So then the initial temperature T1, 25 Celsius, is 298 Kelvin. Add 273 to that to get it to Kelvin. So we have to make that 298. So forgetting to convert to Kelvin is a fairly common mistake on problems like this, or any gas law problem. So don't be forgetting to do that. So if we look at the units, torr cancels out, Kelvin cancels out, and that's going to give us our final answer in milliliters, which comes out to a huge number, 85,570 milliliters, which if I asked for it in liters would be 85.6. So that's a huge expansion. It's going from, 255 milliliters, which would be probably like the size of a softball, to 85 liters, which is like a fish tank. So this would have to be the world's best balloon to not explode under these conditions. But again, just do the math. This is a totally theoretical class, so if the number looks ridiculous, don't worry about that too much, and that's the number that comes out. All right, any questions on that? Yeah.
Would you recommend we convert to liters before we plug it in?
I suppose in this case it wouldn't have been a bad idea because it's a multiple choice question where all the answers are in liters. I forgot this was multiple choice. So yeah, in that case, if you could have converted to liters first, and then you would have directly gotten this number without having to do the final conversion. So it works either way. So it's kind of up to you how you prefer to do that. All right, any other questions? All right, let's just see a few more examples. So this time we have a gas cylinder with fixed volume. So fixed volume tells us that the volume is constant. It's filled with 239 moles of hydrogen, and that gives us a pressure of 136 atmospheres. We add 176 moles, we remove 176 moles from the cylinder. What is the new pressure reading? So this is going to be a relationship that involves number of moles and pressure, and there is no individual gas law that deals with those. So as I said, our universal starting point is going to be PV equal to nRT. In this problem, we're not told anything about temperature, so we're going to assume that temperature is constant. Again, if they don't tell you anything about it, you have to make that assumption. We're telling you that it has a fixed volume, so that means that volume is constant. And then R, of course, is always constant. So these are our 3 constants that are going to be coming out. And so we're going to move those all to one side, and it's going to be pressure and number of moles that are changing. So we're going to divide both sides by N, and then divide also by V. And so what we get is pressure divided by number of moles on one side, those are the 2 that are changing, is equal to RT over V, and that whole thing is constant. All right, so we're going to derive this relationship between pressure and number of moles, which is that P1 over N1 equals P2 over V2. Whatever's changing, we can set this ratio, P over N, equal to each other, because that's what happens when we isolate all the constants to one side. All right, or if you wrote it as N1 over P1 equals N2 over P2, that would be fine as well. Whatever side you move things to is up to you. So that's the relationship we get. And so then when we solve, what we're solving for is the new pressure, P2. So that's going to be P1 times N2 over N1. And so the only thing we have to be a little bit careful about in this problem here is that we're giving you directly the initial pressure. So that's P1. We can use that number exactly as is. We're giving you also the initial number of moles. So this is P1 and this is N1. But for N2, we're not directly giving it to you. We're giving you how many moles are removed, but N2 is going to be how many are left after we've done that. It's however many moles are present. So to get N2, it's going to be the initial amount, N1, minus the amount that we're removing, 176. So we're starting with 239 moles. We're removing 176, so then what's left, the final number of moles that we're going to have is 63. And so what we get then, when we plug everything in, is P1 is 136 atmospheres. Whatever unit we want is fine there. So I got to move this down a little bit. N2 is the final number of moles, which is 63. And then the initial number of moles that we started with is 239. So moles cancel. That gives us an answer in atmospheres, which is 36. All right. In some of these problems, it's kind of hard to, think about it conceptually, because if a lot of things are changing, having an intuition about what would happen is hard. But in this problem, it's a pretty intuitive one. We're removing gas from the cylinder, so the pressure should go down. That feels pretty obvious to me, at least. And so if you had gotten a number that was bigger than P1, you might think that, okay, I probably arranged the equation wrong. Let me check myself. So think about things a little bit, too. I mean, I know the number in the last problem was totally ridiculous, so that may have given you cause for concern, even though there was none. But thinking about the numbers that you get and making sure and double checking yourself if it looks weird is always helpful to do, instead of just typing the number in and moving on with your life. So that's what we get for this one, 36 atmospheres. It does make sense that it's smaller because we removed gas from the cylinder. All right, questions on that? All right, so there's going to be a lot more variations on this same theme on the homework, so I'm not going to go through these over and over and over again, but my advice to you is always start with PV equals nRT, and if things are changing, move the things that are changing to one side, set the before and after equal to each other. And that's going to be an approach that you can take for all kinds of gas law problems, and you'll have a lot of those on the Chapter 8 homework. Now, another related concept that comes out of the ideal gas law is how we can determine the density of a gas. So to sort of calibrate density of water is 1 gram per milliliter. That's a number you should know. And we told you at the beginning of this chapter that gases are way less dense than liquids. The molecules are much further spread out. That kind of makes sense to us. So now we can talk about quantitatively how to actually determine what the density is. And then once we see some numbers, we can see kind of how much smaller they are than the typical density of a liquid. So all we're going to do to find the density of a gas, we're going to get a new equation out of this, but you don't have to memorize the equation because it starts again from PV equals nRT. This is going to be your favorite equation for this chapter. And all we're going to do in this case is go back to things we learned in Chapter 5 and rewrite number of moles in terms of mass. So we learned in Chapter 5 the relationship between mass and moles. Number of moles is going to be mass divided by the molar mass, or molecular weight as it's often called. Okay? Where again, M is the mass in grams. And MW, as we've used many times before, is molar mass. All right, so that's just a way of rewriting number of moles in terms of the mass of the gas. We don't usually talk about mass of gas, but if we're talking about density, we have to. And so then what we do is just say that pressure times volume is equal to mass divided by molar mass times RT. Just make that substitution. And also remember then the density is defined as mass divided by volume. So we move mass over volume onto one side, and then we just separate everything else, and that gives us pressure times molar mass divided by RT. So the density of a gas depends on three things. It depends on the pressure, depends on its molar mass, and it depends on the temperature. So all three of those things determine the density. So you're not going to have a single density for a sample of gas. Nitrogen is not always going to have the same density. It's going to depend on what pressure it's at It's going to depend on what temperature is set as well. But this is just a rearrangement of the ideal gas equation. And the units that are going to come out of this, because we're using typically molar mass in grams per mole, and then R has units of liters in it, it's going to be grams per liter, not grams per milliliters. That's how we usually measure the density of gases. Okay, so that's the equation we're going to use for density of a gas. And so then let's go through and just talk about how to use it. Pretty simple in most cases. So what is the density of ammonia gas, NH3, in grams per liter? That's the standard unit for gas density at 500 torr and 37 degrees Celsius. So we're just going to use that same equation. If you want to learn it, fine. If you want to just derive it from PV equals nRT, it's not too hard to do, as we just showed. And so pressure times molar mass divided by RT. When we're calculating density of gas, this is another one where we're using R in the equation, so we have to make sure we use the right units for pressure, which has to be atmospheres, and of course temperature always has to be in Kelvin. And so we need to convert some things. So we have our pressure is given to us in torr. So another conversion to atmospheres like we did before, divided by 760. So that's 0.658. We need to get the molar mass of NH3, which I didn't give to you here, but we know how to do that from a long time ago. So the atomic mass of nitrogen from the periodic table is 14.01. We have 3 hydrogens, which have an atomic mass of 1.01 or 0.008 if you're being really precise. And that's going to give us 17.03 grams per mole for the molar mass of NH3. And then the temperature needs to be in Kelvin, given to us in Celsius. 37 degrees Celsius is approximately your body temperature. Add 273 to that, and you get 310 Kelvin. All right, so those are the 3 things we need, along with the universal gas constant R. 0.658 atmospheres, converting 500 torr. Molar mass of 17.03. Divided by R, which is 0.0821. And then 310 Kelvin is the temperature. So we get 0.440 grams per liter is what I got numerically. Now you might be looking at the number and say, well, wait a minute, you said that gases are way less dense than liquids, and that's only like a little bit smaller than 1. But remember, the units are different. So water is 1 gram per milliliter. This is 0.44 grams per liter, so it's over 1,000 times smaller. Because in terms of grams per milliliter, this would be 0.00044. So it is a lot smaller. The units are different, so it doesn't necessarily look like that, but that's how we would calculate it. It does depend, of course, on not only the identity of the gas, but also its pressure and temperature, so it's not a fixed quantity for any gas. All right, questions on gas density. So there could also be, I don't think I have one like this in the notes today, but there could be also problems where you have the density of a gas changing or comparing 2 densities and finding molar mass that way. So there's different variations on this, but it all starts from this similar starting point. So definitely do all your homework attempts this week. I always say to do that, but there's a lot of variations on gas law problems. So the more attempts you do, the more of those that you'll see, and then you won't be caught off guard by anything once the exam comes, which really we're going to have 2 exams in a row that cover this material. So it'll be good to have a lot of that practice out of the way. All right. Now the next thing we're going to do a little bit of is talk about gas stoichiometry. So stoichiometry is the old friend that never leaves us at this point in the course. We started in chapter 5, and we had it really involved with everything we've done since then on some level. And same thing here. We're talking about gases now, and we have now some new relationships that involve moles. So the key thing with stoichiometry, of course, is you're relating moles of substances that are involved in a chemical reaction, and you need to know then how to convert into and out of moles depending on how you're measuring those substances and what context you're in. So we talked about previously, chapters 5 and 6, 3 different ways of calculating moles, and which we now abbreviate as N, still just need a number of moles. So number of particles, number of atoms or molecules, entities if you want to do it that way. divided by Avogadro's number, which is 6.02 times 10 to the 23rd. This is the definition of a mole. It's probably the least common relationship we use in stoichiometry, but it does show up from time to time. So that's one relationship involving moles. That was the first thing we covered in chapter 5. The one that we used a lot, especially in chapter 5, was the relationship between mass and moles, which we just covered again in the context of density. So mass in grams divided by molar mass gives you number of moles. So that's another relationship that was very important in a lot of stoichiometry problems. And then in chapter 6, when we covered solution stoichiometry, or titration, which is sort of a spin-off of that, we use this relationship. N is molarity times volume. Where again, M is now, capital M is molarity. So that was an important one for reactions happening in solution, where we define the molarity of the solution, and then at that, the volume give us number of moles. And then finally, what we have in the gas phase is that, PV equals nRT, another one that involves moles. And so for any ideal gas, number of moles equal to pressure times volume divided by RT. Now, one thing that's going to be helpful about this, so in some stoichiometry problems, we can definitely do, we can basically just use this relationship to find number of moles as part of converting into moles of another substance during stoichiometry. But the other thing to realize is that from this relationship, number of moles is also directly proportional to pressure and volume. So if you have a reaction that only involves gases, what's also going to be true is that the mole ratios of the reactants and products is also equal to the pressure ratios. So if you have so let's say we have this gas phase reaction here. The combustion of water in the gas phase. So we might cover this a little bit more later on, but just to kind of give you a little bit of hint of how this is going to go. So from this equation here, it's all gases, and we can say that 2 moles of hydrogen reacts with 1 mole of oxygen to make 2 moles of water. And if we found directly the number of moles of reactants and products, we can relate them to each other in the way that we normally do. But the other thing that we can do when gases are involved is recognize that number of moles is proportional to pressure and volume. And so we could also say, using the same exact ratios, that 2 atmospheres of hydrogen reacts with 1 atmosphere of oxygen to make 2 atmospheres of water. Or in terms of volume, 2 liters of hydrogen reacts with 1 liter of oxygen to make 2 liters of water. So for gases, you kind of have a choice for how you're going to relate the reactants to products. You could always do it in terms of moles, which is the normal way that we do things, but you can also use pressure and volume ratios because they're all directly related to each other. So you don't necessarily always have to convert into moles. You can stay in pressure, stay in volume, and as long as everything's a gas, then those mole relationships are going to still hold when you're defining it in terms of pressure or volume. So we might see some examples where that's useful, but definitely in the homework assignments and reviews that we're going to do leading up to those last 2 exams, we'll see that as well. All right, so let's talk about some gas stoichiometry problems. So we have N2 and F2 combining a 1 to 3 mole ratio at a total pressure of 1.25 atmospheres, and they form NF3. So this is the reaction here. N2 plus 3F2 makes 2NF3. If the reaction is carried out at constant temperature and volume, what is the final pressure at the end of the reaction? So this is kind of like a gas stoichiometry problem, and there's a few different ways that we could approach it. Now, the issue here, though, is we don't know the exact number of moles that we have. We just know the ratio, and we know the initial pressure. So what we're going to do for this type of problem is start with PV equals nRT. And basically, we're just going to recognize that in this problem here, the number of moles of gas is changing because we're doing a reaction. And we see that on the left side of the arrow, there's 4 total moles of gases, 1 plus 3. On the right side, there's only 2. So as these 2 things react with each other, you're going to change how much gas you have because you're forming different numbers of moles of products than you started with. So number of moles is changing, but we're telling you that temperature and volume are constant. So we're actually going to just approach this a lot like we did the last problem, where we're going to find everything that's constant and move it to one side. So in this case, pressure and number of moles are changing. RT over V is constant. And so the nice thing is we don't necessarily need to know exact quantities for everything because we're just going to establish a relationship between pressure and number of moles. So this is kind of just an ideal gas problem disguised as stoichiometry because in this case here, if we just want to know what the final pressure is, we just need to know how do the initial and final number of moles relate to each other. So our final pressure, P2, is going to be P1 times N2 over N1. And the way that we're going to define these things is N2 is going to be how many moles are left at the end of the reaction, which is the moles of product. And N1 is the moles of reactant. Because for these ideal gas relationships, we actually don't care what the identity of the gases are. All gases follow these relationships. So even though we're changing nitrogen and fluorine into NF3, we have different gases involved, all we really care about is the ratio of the number of moles, because that's going to give us the new pressure. And so we can just start plugging things in here. We have 1.25 atmospheres as our initial pressure. And then N2 over N1, we don't know the exact number of moles of gas we're using, but we're telling you that we're combining them in a 1-to-3 ratio. And so that means they're going to react completely to form the product. And so what we're starting with on the reactant side is 4 moles of gas, and we're ending up with 2 moles, as we already said. So we're going to put 2 moles of gas in for the product, and then 4 moles for reactant. We don't know if these are the exact numbers, but they're always going to be in the same ratio because of the coefficients from the balanced equation. And so that comes out to 0.625 atmospheres. So that was a little bit of a weird one because it sort of involves stoichiometry, but in reality it was just an ideal gas problem, because all we're doing is just doing a chemical reaction to change how many moles of gas we have, and just using the relationship between pressure and number of moles that we can derive from PV equals nRT. So that one's a little bit odd in some ways, but it's you know, it's sort of related to stoichiometry. So any questions on that before I get a more typical one going? All right, so the more typical one is going to be shown here. So we're going to do this following reaction at 400 Kelvin. We're going to take phosphine PH3, react it with oxygen, and make P2O5 and water vapor. All right. And so here's how you do a gas phase reaction, just if you're wondering. So you would have a valve of one gas labeled A here, that's pH3, a valve of a second gas, or sorry, a bulb, I guess is a better way to say it. A bulb of one gas pH3, a bulb of a second gas O2, and they're connected in the middle with a valve that sort of separates them from each other, called a stopcock. Please don't laugh. And so we have this valve here, the C, that's connecting the two, so they're initially separated from each other. You open up that valve, and that allows the two gases to mix together. Remember, gases are going to fill all the available volume. So once you open this valve C here, you know, pH3O2, they're going to diffuse all around, mix together, and then this reaction is going to happen. And they're going to occupy the entire space that's available to them, as all gases would. So what we're doing here is we're taking 12.5 liters of phosphine at a pressure of 2 atmospheres. That's bulb A here. We have 10 liters of oxygen in B, initially at a pressure of 3 atmospheres, and they're initially closed off by this valve here, C. So how many moles of gas are present at the start of the reaction? So for this, we just have 2 gases, pH3 and O2, and we're just going to use PV equals nRT to find how many moles of each gas there are. So we're going to kind of do this in a few steps here, but just see all the different things we can do with this now. So number of moles is PV divided by RT. We just rearrange the ideal gas equation. And so for phosphine pH3, we're told that that's bulb A here. So the initial pressure of that is 2 atmospheres. The volume of that bulb is 12.5 liters. That's the bigger of the two. And then we have R and C in the bottom. Because we're using R, it has to be atmospheres and liters, which is already given to us, so we don't have to do any conversions. And then the temperature is 400 Kelvin. Again, also given to us in Kelvin. So no unit conversions needed here, we just have to plug everything in. And we get 0.761 moles of pH3. Now we'll do the same thing for O2 using its pressure and volume. So the pressure for O2 was 3 atmospheres. They're separated initially, so they're at 2 different pressures. They can be anyway. And then the volume of that container where O2 was initially present was 10 liters. Same universal gas constant, same temperature at the bottom. So we get 0.914 moles of O2. Okay, so that's the moles of each gas. So in a gas stoichiometry problem like this, where they're initially at different pressures, different temperature, they're at the same temperature, but different pressures and different volumes, this is the way that we can find moles of each as our starting point. All right? So that's going to be the first part. The second part is when this valve C is open and the gases mix and are allowed to react, which gas is a limiting reactant? Okay, so now it becomes just a stoichiometry problem because we know moles of each gas, and we just need to find which one's the limiting reactant as sort of the next step that we're asked to do. So we just found that for pH3 phosphine we have 0.761, and then for O2 we have 0.914. As we talked about a lot in chapter 5, just knowing the number of moles does not identify the limiting reactant. You also have to find what I call the stoichiometric ratio, where you're going to take that number and divide it by the coefficient. So for pH3, 0.761 is the number of moles, and the coefficient in the balanced equation is 2, so we're going to divide by that and get 0.38. And then for O2, we do the same thing. We take its number of moles, which is 0.914, and then divide by the coefficient for O2, which is a 4, and that comes out to 0.23. So the one that's smaller is our limiting reactant, and that means O2 in this case will be the limiting reactant. As it turns out, this is a horribly stupid way to carry out this reaction because you're trying to convert an awfully toxic gas pH3 to something that's essentially non-toxic, and you're not using enough O2 to do that, so good job. But anyway, O2 is a limiting reactant, so don't worry about the stupidity of the person that set up this problem, which may or may not be me. And then that's how we would do it, though. Just find the number of moles like we did in the first step, divide by the coefficients. It's just stoichiometry at this point, nothing new. All right, and then another question we could ask is how many grams of the product, P2O5, are formed. So this is a solid, so we're not going to be able to determine what its pressure and volume is like we would for a gas, but we can just use stoichiometry to find grams like we always would. So the grams of P2O5, we start with moles of limiting reactant, O2, 0.914, the number that we found earlier. And we just use now coefficients to find out how many moles of P2O5 would form from that. So P2O5 has a coefficient of 1, so that goes in the top. O2 has a coefficient of 4, so that goes in the denominator, so it cancels out. So O2 cancels out. And then what we're going to do is multiply by the molar mass to get it back into grams. So this gives us moles of P2O5. We want grams, and so we use molar mass. We get 32.4 grams. So we just use PV equals nRT to find moles of each gas. After that, it's just a stoichiometry problem, nothing new for us. So that's where we're going to stop for this one. There's actually one more part to this problem that I no longer do because it just takes a long time and I spend like 10 or 15 minutes just doing one thing. But if you want to challenge yourself or you want to talk to me about it afterwards, how you would do this, or figure it out for yourself and see if you did it right, the other thing that you can now calculate is what is the total pressure after the reaction is over. Now that's going to require us to learn what we're going to learn now first. So at the end of today's class you'll be able to do it. But the last step, which is again something that we haven't quite covered yet, but you could do it in principle, is okay, after the reaction's over, we've formed some water vapor, we've consumed all of our oxygen because it's a limiting reactant, we have a little bit of this left over. The new volume is the combined volume of both bulbs. All that information that we now have, you could be able to calculate the final pressure. So that's something else you could try as well on your own. That's probably a step beyond what we'd ask you to do in an exam, but if you can figure that part out, then it seems you have a pretty good grasp of a lot of these topics. All right, so there's a lot more to this that I'm not going to do because it takes forever. What we're going to move on to now, if there's not any last questions on that, is what's called Dalton's law of partial pressure. So we did learn something else that Dalton did a while ago. So Dalton also came up with the atomic theory, which was the initial, propositions about matter being made up of atoms, and it was used to explain the three mass laws that we learned way back in chapter 1. So Dalton was responsible for that. He's also then did a lot of studies on gases that led to this law of partial pressures. So first we're going to just do a thought experiment to see a little bit about how this works. All right, so let's say we have a flask filled with 1 atmosphere of nitrogen. You add to that flask an additional 1 atmosphere of nitrogen. What is the total pressure? So 1 atmosphere, 2 atmospheres, 0 atmospheres, or D, who cares? Any, just shout a letter if you think you know it. B. Okay, it's not a trick question, exactly. So whenever you have a gas at some pressure and you add more of that gas, the pressures are additive, so you just add them together. Now let's say we have the same flask that has 1 atmosphere of nitrogen, but now we're pumping in 2 atmospheres of a different gas, O2, so it's not just one gas anymore, it's 2 different gases. What will be the total pressure in this case? 1 atmosphere of nitrogen, 2 atmospheres of O2, what's the total pressure? C, right, there's nothing tricky about it. Even if it's 2 different gases, because they all follow the ideal gas law, the pressures just add up together, okay? And so that's kind of the basis point then of Dalton's law of partial pressures. Pressures are additive. And the reason for that is because gases mix homogeneously. So when you mix 2 gases together, they don't separate into 2 different phases or avoid each other. They mix completely together. Just like the air we breathe is a mixture of, mostly oxygen, mostly nitrogen, a few other minor components, and it all just mixes together as one homogeneous unit. And the other thing to realize is that, each gas in a mixture, so if we have a mixture of 2 or more gases, each gas behaves as if it's the only gas present. So it doesn't care that there's another gas around it. It just behaves as if it's on its own. And that means we can define, as we'll talk about, what are called partial pressures for each gas. We don't have to worry about necessarily the total pressure of the mixture all the time. We can define the individual pressure of each gas as if it were the only gas present. So the fact that in this second scenario here, the fact that nitrogen is mixed with oxygen doesn't change individually the behavior of nitrogen or oxygen. The total pressure is the sum of the two, but nitrogen still behaves as if it's 1 atmosphere of nitrogen, and to still follow PV equals nRT as if it was still by itself. Oxygen would still behave as 2 atmospheres of oxygen without nitrogen presence. They don't care that the other gas is mixed with them. All right, so that's going to be the case with Dalton's law. Now, it's not always going to be just as simple as adding 2 numbers together. We're going to learn some other mathematical relationships that come from this, as well as some different applications of it that we have to go through. But this is really the conceptual basis of all of it. So let's talk about then the equations that come out of this. So in terms of pressure, here again what we're talking about is a mixture of 2 or more gases. That's kind of the scenario we're picturing here. So the total pressure of the mixture, as we talked about already, is just the sum of the individual pressures of the gases that mix it up. Where when the gases are in a mixture, we call them partial pressures. So however many gases you're mixing, these pressure A, pressure B, pressure of C are all called partial pressures. And so if you know the partial pressure of each gas, you just add them together to get the total pressure. It's as simple as that, just like we talked about. Now that said, sometimes we're going to do this in terms of how many moles of each gas we have. And so if we rewrite this relationship in terms of moles, pressure is equal to nRT over V. And so that means if we have a mixture of gases, the total pressure is going to be the moles of the first gas we have times RT over V plus the moles of the second gas we have times RT over V. Oh man, let's do this again. Every like 2 weeks it does this and never. So for those of you that are watching at home and wondering why I just spazzed out, it's because my tablet froze again. Well, not the tablet, the stylus. And so we're going to have to do a quick reset. And you guys get an unplanned break, so take a breather. All right, picking up where we left off when my tablet rudely interrupted us. So what we're doing here is rewriting this in terms of number of moles of each gas. So you would have the total pressure is the moles of the first gas times RT over V, moles of the second gas times RT over V, moles of the third gas times RT over V. And since when we're mixing 3 gases together, or however many gases we have mixed together, they're all going to occupy the same volume because they're all mixed together in the same container. and they're all at the same temperature when they're equilibrated with each other like that. So basically what we can do is we can factor out number of moles and just say that this is equal to the total number of moles times RT over V. So if you want to find the total pressure of the system and you have the moles of each gas, you just need to add up the number of moles of each gas to get you the total moles, and then times RT over V gives you the total pressure. So similar relationship. Now the sort of new thing that comes out of this is what's called mole fraction. And it kind of derives from the one above it, but basically the net result of this is that if you want to find the partial pressure, so a lot of times what you have is the total pressure is something that you can measure that, and you want to find what's the pressure of one of those gases in the mixture, A or B or C or whatever, however you label it. And so that's going to be given as this new parameter here called chi, mole fraction, another Greek letter for our alphabet, times the total pressure. Where the mole fraction of a gas in a mixture is going to be the moles of that gas divided by the total number of moles. And again, we call that mole fraction. So this is another sort of concentration unit, kind of like molarity. It's more useful for mixtures of gases where you know the moles of each than it would be for aqueous solutions, but it's just, again, a way of sort of reporting the composition of that mixture in terms of one of the gases. And the reason this works as sort of a quick and dumb proof of this is that, as we said, the total pressure is the sum of the partial pressures. And we're telling you here that the partial pressure is equal to mole fraction times total. So for each gas, it's going to be their mole fraction times the total pressure. And then we can factor out the total pressure because there's the same total pressure for the whole mixture. And so it's just going to be chi A plus chi B plus chi C times the total pressure. And when you have a mixture of any substances, the sum of the mole fractions equals 1. They all add up to 1. And so that's just 1 times the total pressure. So I guess if I was pompous, I would say QED, but basically that's a way of demonstrating that that's true. So that's this down here is just a stupid proof. Don't worry about that. This is the equation that's going to be most important for Dalton's law, as well as the recognition that, if we have mixtures of gases, if we have the moles of each, then there's these relationships as well. So that's going to be some equations that we'll use for Dalton's law. So let's just see then how it works. So one application of Dalton's law is just doing exactly what we talked about, determining partial pressures of gases in a mixture. So we have a mixture of gases that has 40 grams of oxygen and 40 grams of helium and a total pressure of 0.9 atmospheres. What is the partial pressure of O2? So whenever you're calculating partial pressure, you immediately want to think about that relationship that we just gave, which is that the pressure of that gas, the partial pressure, is equal to its mole fraction times the total pressure. So the total pressure here is given to us already, so we don't have to do anything to find that, but we do need to find the mole fraction of O2. So mole fraction, as we just defined, is going to be the moles of that gas divided by the total number of moles that we have in the mixture. The mixture is only 2 gases, so it's just going to be the moles of oxygen divided by the moles of oxygen plus moles of helium. That'd be the total. So in this case, we're not given moles, we're given grams, but we know how to convert, so we don't have to worry about that too much. We're just going to find the number of moles of each gas starting with the masses. So for O2, the molar mass is 32, 2 times oxygen. And so that gives us 1.25 moles of O2. And the moles of helium here is going to be same mass in this case. The atomic mass of helium is 4 from the periodic table. So I won't flip back to that, but that's what you'd get. And that's going to be 10 moles. All right, so that's the moles of each gas. Now we can calculate the mole fraction of either of them. In this case, we want O2. So for O2, it's going to be 1.25 moles, which is how many moles of that gas we have, divided by the sum of the two, 1.25 plus 10, which is 11.25. And then the fraction comes out to 0.111. Okay, so that's our mole fraction of oxygen. So we're going to put that up here then, multiplied by the total pressure. And we get 0.0999. So actually most of the pressure in this case is from helium. You know, there might be a temptation to say, well, we have equal numbers of moles of each gases, so you know, that should mean the pressures are equal. Well, as we talked about, the partial pressure doesn't depend on how much gas you have in terms of mass, it's about how many moles you have. So we have equal numbers of grams, but we have more moles of helium, so most of the partial pressure would come from helium. All right, so that's going to be the final answer there, mole fraction times total pressure. All right, any questions on that? All right. Now, one other application of Dalton's law, I gotta make sure I don't really lose track of time, we're so good. There's another type of gas stoichiometry, or an application in gas stoichiometry that uses this Dalton's law of partial pressure. So this is kind of a very specific niche problem type. I don't know why general chemistry textbooks love it so much, because I've never actually done something like this in the lab. Although in principle you could. I doubt you do it in our chemistry lab because it involves like setting things on fire and all that stuff. But anyway, if you have a reaction that produces a gas, we can use Dalton's law to help us measure how much gas is produced. So we've talked about stoichiometry a lot, and in chapter 5 it was okay, we're measuring out masses of each reactant and product, and that's how we get the amounts. And then in chapter 6 was, well, we have aqueous solutions, we can do volumes and molarities. If you're doing a reaction that involves gases, or especially one that evolves a gas, this is a way that we can measure it and quantify it and sort of see what our percent yield is or whatever it is we're looking for. So let's just go over the experiment first that we're setting up, even though, again, this is just going to be done as a word problem. So the first thing we're going to do a reaction here where we're going to heat up a mixture of, in this case, we're just showing it as potassium chlorate and manganese oxide. It doesn't really matter that much, but basically when you heat these up, you produce oxygen as a product, O2, okay? And so what you have here, I'm going to label these with different numbers. Over here you have a reaction that produces a gas. And basically the flame here, the Bunsen burner, is just to heat them up and get the reaction going. If you just mix the two powders together, they'll just sit there and stare at each other. They need a little bit of energy to get going. We'll talk about that in Chem 2 as well. And then what we have is so the oxygen is produced in this test tube, and it's going to carry through this glass tube here to the other side. Okay, because again, gases diffuse, they fill the available volume. And so the gas is going to be transported to the collector. And then finally over here in the collector, which is going to be labeled with number 3 here, the way that we're measuring how much gas is produced is that the gas is going to bubble up into this headspace here. It's going to displace some of the water. So basically the water that's in this inverted jar here, that level is going to drop as more and more gas goes up there. You're going to drop the level of the water, and then if you measure that, how much it drops, the volume of that it changes, that'll tell you how much volume of gas you produced. So this is kind of a low-tech way of measuring gas volumes. So the gas is going to displace the water in the collector. And by measuring how much the volume of that water changes, how much it drops as the gas goes in and pushes it down, you can figure out the volume of the gas that was produced. Now the issue here though is, so what you're going to then do is you're going to measure the volume of the gas that's produced. You're going to know the pressure of the whole system because you measure that with a barometer. So we have pressure, we have volume, we know the temperature. Okay, so that gives us ideal gas law. We can find number of moles of that gas. So basically you're going to use this to find number of moles of gas. The one little catching point though that you have to be aware of is that, and this is where Dalton's law comes into play, when you collect oxygen up here, it's not just going to be pure oxygen. There's going to be also mixed with water vapor because it's above the surface of water. So we'll talk more about vapor pressure and that kind of stuff in chapter 9. So this will again kind of all come together after we've gone through all of that. But basically what you have is above this surface of the water, you don't just have oxygen, you have also some water molecules that are in the gas phase. Anytime you have a liquid, you're going to have some of those molecules from that liquid escaping the surface and being in the gas phase right above it, and creating then some pressure of their own. And again, chapter 9 will cover that in more detail. We're kind of already familiar with that. You know that water evaporates if you leave it out. We have humidity, of course, around here especially, so that's just water vapor all in the air. So that's always going to happen. And so above this collector, you're also going to have to account for the vapor pressure of water. So some small percentage of water molecules escape the surface of the liquid. Again, not very many. Most of it stays in the liquid phase, but some small percentage escapes the surface and create a small partial pressure above that surface. So the value of this pressure is temperature dependent. So we'll learn in chapter 9 how it's calculated. In this part of the course, we're just going to give you the partial pressure of the water. The number that we give you will depend on what temperature we're setting up for the problem, but it'll be given to you. But you have to know what to do with it. You can't forget about it. So as we go through an example problem of this type, basically, we're going to see that if we don't account for the vapor pressure of water, we'll get an answer that's close but not quite. And that's the most common mistake people make, is to forget about this water vapor pressure or know what to do with it. Okay, so let's talk about then an example of this exact situation. So acetylene, which is used often in torches, C2H2, you can produce it by mixing water with an ionic compound called calcium carbide. We didn't really talk about carbide ions before, but that's one type of compound, CaC2. And you can mix it with water, and that releases acetylene gas and leaves behind calcium hydroxide. So you're going to produce this gas and then collect it and measure it. So we collected the gas over water at 23 degrees Celsius, and the total pressure of the system is 738 torr, and the volume that we collected is 523 milliliters. If the vapor pressure of water is 21 torr at this temperature, how many grams of acetylene were produced? So the key to doing these problems, we already have the volume, we already have the pressure, we already have the temperature. So like if we're just looking for grams, we just, find number of moles, multiply by molar mass, done. But we have to remember that there's this small amount of water pressure. And so this total pressure that we're measuring here is really a sum of both of those. This is where Dalton's law comes into play. So it's the pressure of the gas we're producing, in this case C2H2, that's what we want, but that total pressure also includes the water vapor pressure. So what we have to remember then is to subtract to find the partial pressure of the gas that we're interested in, C2H2 acetylene in this case. So it's going to be total pressure minus water vapor pressure. And so what we find is that the total pressure is 738 torr. The vapor pressure at this temperature is just 21. Again, it's a pretty small quantity in general. And so that gives us 717 torr. So if we just use 738 as our pressure, we get an answer that's close. 738 and 717 aren't that different from each other. But we have to remember to account for the water vapor pressure and subtract it out so that we get the pressure of just the gas itself that we're trying to measure. All right, so if you forget that step, you might do a problem, you're like, oh, but I was really close. Why didn't it count my answer right? Well, it's probably because you forgot to do this. You will be really close because these numbers aren't that different from each other. But to get it exactly right, you need to account for the water vapor pressure. So now that we're ready to do this, we have everything we need because we have the pressure of just the gas itself, and we can use the ideal gas equation to find number of moles. So what we have is the number of moles of C2H2 is its partial pressure times the volume divided by RT, just rearranging the ideal gas law, and now we have all the numbers that we need. This requires us to use R, so we're going to have to put that into atmospheres. So the pressure in atmospheres of C2H2 is 717 torr. That was the partial pressure we calculated from Dalton's law, subtracting the vapor pressure, and we divide by 760. Get 0.943. So that's the partial pressure The volume of the system is 523 milliliters. That needs to be in liters for the ideal gas equation. So 0.523, and then RT in the bottom. 0.0821 liter atmospheres per k mole. And a temperature of 23 degrees Celsius, which converts up to 296 Kelvin, adding 273 to that. All right, so don't forget your temperature units still. So we had to have the right units because we're using R in the equation, and that gives us then 0.0203 moles. Okay, so that's how many moles of C2H2 we produce. The question is asking for how many grams, so we need to use the molar mass now to get the number of grams. So we just need a little bit more space, so we're just going to do that here. 0.0203 moles of C2H2. And its molar mass, I believe I gave it to you in the problem. I did 26.04. Grams in 1 mole. And that comes out to 0.529 grams. All right, any questions on that one? So you'll see problems like this on homework assignments and tests. It's the same, pretty much the same set of steps every time, but you just have to remember to account for the water vapor pressure, and this is what we do with it. All right. Then I guess last problem dealing with this one. This is just a review of stoichiometry, so nothing big here. If we assume 100% yield, how many grams of the calcium carbide do we need to produce that much acetylene? So at this point, it's just stoichiometry. We already know how much gas we produced. The other reactant's a solid, so we're not going to do anything with the ideal gas law for that. We're just going to do a quick stoichiometry conversion to figure out how many grams of calcium carbide were required for that. So we just found that we formed 0.203 moles of C2H2. Or we could have started with the grams of C2H2, but then we have to convert it to moles anyway. So we already had that number from before, so we'll start with that. That's how many moles of product we formed. And then we just have to use mole ratios to figure out how many moles of calcium carbide, CaC2, that requires. So 1-to-1 mole ratio, so just multiplying by 1. So that cancels out moles of C2H2. That tells us how many moles of the starting material, the reactant that we needed, and then we're going to use its molar mass to convert that to grams. 64.1 grams of CaC2 in 1 mole. So moles cancel out. We're in grams now, and we get 1.30. So if we take 1.30 grams of calcium carbide, react it with water, collect all the gas, that's how much we get, is what we calculated above, 0.529 grams of acetylene, C2H2. All right, so there's some things here that kind of reviewed stoichiometry. Dalton's law comes into play for problems like this. And so again, there's a lot of, chapter 8, the math is not too difficult. There's not too many concepts like there was in chapter 6 and 7, but there's just a lot of different variations on the problem. So it's going to be especially critical in this part of the course to do as many practice problems as you can, to just get familiar with all the different ways we can set them up. There's no new starting points for you, but you just have to know what to do with all the information. All right, so we'll end there if there's no last questions, and then on Thursday we'll plan to finish chapter 8. I don't know if we'll start chapter 9 also, but definitely finish this chapter, so be ready for the assignment this week and move on into then the last chapter of the course.
Well, now